Okay, well, welcome everyone to this distinguished lecture series as part of the Mathematics of Data Science initiative by SIAM, which is the Society for Industrial and Applied Math. We are honored today to have Cynthia Dwork as our speaker. Cynthia is the Gordon Mackay Professor of Computer Science at Harvard and the Radcliffe Alumni Professor at the Radcliffe Institute for Advanced Study. She's renowned for seminal contributions in cryptography, distributed computing, and statistical validity, which are all mainstays in theoretical computer science. But quite incredibly, she's also well known for her contributions to many societal aspects of this algorithmic world that we live in. Her current focus is on algorithmic fairness, where she is one of the originators of this very influential notion of fairness known as multi-calibration. And she's also one of the originators and the original inventors of differential privacy. And she's renowned for placing privacy preserving data analysis on a mathematically rigorous foundation. That's going to be the topic of our talk today, which is going to be on differential privacy, the mathematical bulwark against re-identification and reconstruction. She has won numerous awards. She's a member of the US National Academy of Sciences, the US National Academy of Engineering, the American Philosophical Society. She's a fellow of the American Academy of Arts and Sciences. Her recent awards include the 2020 IEEE Hamming Medal and the 2020 ACM IEEE Knuth Prize. So without further ado, I would like to introduce Cynthia Dwork. Also, if you have any questions, please ask them using the Zoom Q&A. Thank you.
Thank you very much, Ashish, for that lovely introduction. And thank you to the organizers of this very exciting new conference for creating the conference and for inviting me to speak at it. I need to say one thing. I am a big enthusiast of multi-calibration, but that particular idea is due to Aber Johnson, Kim, Reingold, and Rothblum. And while I'm an enthusiast, I'm not an inventor. So, this talk in a nutshell. This is a talk about privacy. So when we think about privacy preserving data analysis, we have sort of two notions in mind. There's understanding the population as a whole and finding a needle in a haystack. And we need to differentiate between them. So for the first category, we have statistical understanding of the population. So that would be, for example, in the census, or maybe analyzing loan data for evidence of systematic discrimination, or maybe even in machine learning as we train a classifier to distinguish images of healthy brain cells from cancerous ones. On the needle in the haystack, we would have something, let's say, as the Total Information Awareness Program was, which was aimed at finding terrorists in the data of lots and lots of people, most of whom were not terrorists. So differential privacy is a tool for the first kind of analysis. It is absolutely the wrong tool for the second one. So if you're trying to find some notion of privacy and some methods for adhering to that notion of privacy that will find you a needle in a haystack, you need to look elsewhere. Differential privacy is not the solution that you would be looking at. Okay. Now, so we want to do statistical analysis of a population. So statistics feel private. Statistic is a quantity that's computed from a sample, and it tells us about the population as a whole. And it feels private in the sense that, well, sort of if you had two data sets that were collected independently from the same population and with correct methodology, you would expect them to tell us essentially the same things. And so an individual who might be in one of the samples might not even be in the other sample. And so clearly what the other sample says is sort of not about that particular individual. And the sense of privacy is probably derived from this fact. No one knows whether I'm in the sample or not. I can claim that I opted out. In these senses, what's learned is not about me. So this is basically on the right track for getting toward a definition of privacy and an approach, but it needs help. And differential privacy provides exactly that help. So differential privacy is in fact going to give statistical, that sort of feeling of privacy, that I could have opted out notion for all computations, even on total population counts. And that's a little surprising. So we'll return to the notion of census later. It's going to be important to us. So how do we abstract this problem? Here's our abstraction. This is a very, very broad abstraction. So roughly speaking, on the left, we have a database. On the right, we have a data analyst. The data analyst might be very well intentioned, or she might be just trying to break people's privacy and doesn't care about actually analyzing the data. We don't know, we can't tell. And in fact, we want to be sure we don't have to care. And our analyst will interact with the data set by sending a query and getting an answer. And then maybe, depending on the outcome of the first query, choosing a second query and sending up that follow-up question and getting an answer to that question, and so on and so forth. So this is so broad because it could be that the questions that the data analyst has are fixed in advance, and she could pack all of them into that first query, Q1, and say, please give me the following statistical analyses. And then she would get her privacy preserving answers, A1, to all of those analyses, and then that would be the end of it. Or perhaps they really will interact over time. Or maybe the data analyst doesn't know what she wants to know yet. And so she says, hey, try to give me a table or a blob of some sort that will let me extract the answers to questions that I will figure out later. So give me noisy data, for example, that protect privacy. So the form is very, very broad. And the driving scenario for this work was actually analysis of US Census data. Our feeling when we started this in about the year 2000, 2001 was that census data is data that belong to the people, and they are analyzed in order to apportion the people's resources for the benefit of the people. And moreover, privacy of census data is legally mandated. So that was the driving scenario for us, that there had to be privacy. But it's a very, very old problem. Okay. So this will be a running example, flossing. So the secret information that we're trying to understand about our population is kind of what fraction of people floss regularly, but not necessarily whether you personally flossed last night. So you might say that if you want to ask, sorry. Okay. So one possibility is to say, well, we just want statistics. So why don't you tell us something about, say, what fraction of the people actually flossed last night? And the problem with sort of just having statistics is that you can create what we call a differencing attack. So suppose we have a database and we ask the database, how many living physics Nobel laureates floss regularly? And we get the exact answer to that. And suppose we then ask, how many male living physics Nobel laureates floss regularly? And we get the answer to that as well. In that case, by subtracting one from the other, we would be able to determine whether Donna Strickland flosses regularly or not, compromising her privacy. So that differencing attack is just a little toy example of a very important principle, which is sometimes called the fundamental law of information recovery, or the database reconstruction theorem. And what it says is intuitively that overly accurate estimates of too many statistics is blatantly non-private. So we just saw an example of being able to reconstruct the flossing bit by having perfectly accurate estimates for two statistics. If you, in general though, the definition of overly accurate changes with the definition of too many. If you want to ask many, many queries, you have to have more and more inaccuracy. If you want to handle just a few, you can get by with less inaccuracy. But one thing that's known is that one of the consequences of this thing is that this theorem is independent of the form in which the answers to the queries are delivered. So remember that idea that I mentioned before of maybe just publishing some sort of blob that would allow the data analyst to decide later what she wants to ask and get accurate answers to all of those questions? Well, if I publish a blob that is going to give very accurate estimates to lots and lots and lots of statistics, because there are many statistics that this adversary or analyst may choose to ask later, then the analyst can carry out a reconstruction attack against this blob. So this is a very, very powerful result. And in fact, you can't even publish a blob that makes it possible to answer all queries up to about sampling error, not all queries, sorry, for even more than a 1 minus 0.29 fraction of those queries relatively accurately, with the remainder wildly inaccurate. So the fundamental law is what we are up against. It's completely independent of differential privacy or any other technique one might try to use. It just sort of says, you can't answer too much too well. Okay. So the definition of differential privacy. This is a picture of Cecilia Helena Payne-Gaposchkin, and she was among the first women to obtain a PhD in astronomy, and she was the first person to obtain a PhD in astronomy at Harvard. And she ascertained the temperatures of different classes of stars and estimated the great abundance of hydrogen in them, much more than Earth, while doing the research for her dissertation, contradicting the belief at the time that the sun and the Earth had similar compositions. So the question is, how should we define privacy? Definitions are essential, and without them, we literally don't know what we're talking about. So what would we mean by privacy preserving data analysis, and what kind of protection should we offer to Cecilia Payne? So a natural candidate, and certainly the one that I first tried, was articulated by Tour de Linnaeus in 1977. And it says that the data analyst can't learn anything new about Payne that wasn't already known beforehand. For example, Payne could be an extrovert and she could publish a lot about herself on her website. That's fine, but we don't want to publish the statistical database for things that are already public. We just don't want anything new to be learned. And the problem with that is, then what's the point of our database? So to drive this home, suppose I'm from Mars and I incorrectly believe that all humans have 2 left feet. And so in particular, I believe that Payne has 2 left feet. And then I do some analysis using this statistical database, and I learn that the vast majority of humans have 1 left foot and 1 right foot. So now I've learned, in some sense, something new about Payne, and my view of her has changed. So the question is, have I compromised her privacy? So going back to that opted in, opted out intuition, ideally I would have learned the same things if Payne were replaced in the database with Henrietta Swan-Leavitt. She was the first to note a relation between certain variable stars' peak brightness and the period over which their brightness varied, which provided a valuable means for measuring distances across space. So we simply took it as axiomatic, as definitional, that this is not a privacy violation. That if we could have learned the same things about Payne, had she been replaced with Swan-Leavitt, then this is not a privacy violation of Payne. And so that brings us to the English language definition of differential privacy. which says that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. And in fact, we might even have a scenario where the data analyst knows knows that the database is one of two, either the one illustrated at the bottom or the one illustrated at the top, which is the same as the one at the bottom, except we've added pane. And even knowing that, with this definition in blue, if the outcome of the analysis is essentially equally likely, given the outcome of the analysis, the adversary cannot tell which of these two worlds is in fact the true world, which is the true database that's being analyzed. Okay. So an adversary knowing both data sets in their entirety can never distinguish, not now and not given any other information from any other source external to the data set. So when we say that the outcome of any analysis is essentially equally likely, we have to say what's the source of uncertainty in unlikely? What is the experiment? And the answer is that our algorithms will flip coins. They will randomize their outputs. They will add some kind of noise, and the distribution of the noise is key to ensuring privacy. Okay. So just to emphasize this, suppose we have a fair coin, and on one hand, and we have a second coin which is very slightly biased. So this one has probability 501 over 1,000 of coming up heads rather than 500 over 1,000 for the fair coin. And given one of these coins, and you don't know which one, there's some flipping algorithm that flips the coin and produces either heads or tails. Then the probability distribution on the outcomes is nearly the same for the two coins. The probability of heads is nearly the same for the two coins, the probability of tails. And in fact, even seeing a couple of flips, you really don't know which is the actual coin. That's the kind of privacy that we're going to ensure. Okay. Now, with this really strong definition of privacy, you could say, why is it possible to do any kind of data analysis at all? So it's just a remark that we usually think about privacy and utility being in conflict with one another. But differential privacy, this kind of, you would learn the same things even if the database changed slightly, is a notion of stability. And it not only preserves pane's privacy, it also prevents overfitting. So, in fact, differential privacy will protect against overfitting and p-hacking, but that's, we may or may not get to that during this talk. Okay. So instead of privacy and utility always being in conflict, if we think of the utility as being how can we generalize from the sample to the population from which the sample was drawn, then privacy and generalization turn out to be aligned. Okay. So now we're ready for the mathematical definition of differential privacy. Our algorithms are called mechanisms for historical reasons and usually denoted as M. And there's a privacy loss parameter. So privacy is not binary. It's not either private or not private, but rather there is a quantity of privacy, and that is captured by the parameter epsilon. And we need the notion of a pair of adjacent data sets. So two data sets are adjacent if one of them is contained in the other and the larger one has the data of just one more person. So the database as a whole, and then the database plus the data of Henrietta Swan-Leavitt would be adjacent pairs. So differential privacy says M, our algorithm, gives epsilon differential privacy if for every pair of adjacent data sets X and Y, and every possible output event S, the probability that we observe S when the database is running on, when the database is X, is at most e to the epsilon times the probability that we observe S when M is running on Y. And the definition, X and Y are, the definition is symmetric. So we get the other inequality as well. And we can think of epsilon as a bound on what we call the privacy loss, or it's a bound on the ratio of the probabilities of two different observations, or rather the log of the ratio of the probabilities of seeing two different, S on two adjacent databases. And the probability space in both cases is the randomness that's introduced by our machines, our algorithms. So differential privacy is a worst case notion over all pairs of adjacent data sets and all outputs S. Okay. So for those not comfortable with e to the epsilon, when epsilon is small, this is about 1 plus epsilon. So we can see that the smaller epsilon is, the less information is being leaked by the observation S about whether the database is X or is Y. Notice that this is a statement about the behavior of the algorithm M. And this, it doesn't care who knows what the analyst or the adversary actually knows. Not only now, but even in the future. This is simply a flat out bound on behavior. So you can learn things about pain. For example, you can learn that pain, like most people, is likely, like if she's like most people, she probably has one left foot and one right foot. But you can only learn things about pain that you could have learned even if she hadn't been in the data set. So differential privacy says you are free to go ahead and carry out machine learning and understand your population, but you shouldn't learn things about an individual that you would not have learned had they not been in the training data. Okay. And this is why differential privacy hides the needle and is the wrong tool for finding a needle in a haystack. If our database is X, including the needle, and when we take away the needle, we get the adjacent database Y. The whole point is that the adversary can't tell whether the database is X or Y. If you can't even tell whether the needle is there, you don't learn about its properties. So the key properties of differential privacy, independent of how you implement it, so following straight from the definitions, is first and foremost, it is future-proof. So it's resilient to any present or future information from other sources. If the algorithm is differentially private, that differential privacy is not compromised when one learns information from sources other than the data set. Differentially private algorithms compose gracefully and automatically. So what that means is we can understand and control, it turns out, the cumulative privacy loss over multiple computations. And at worst, the losses add up. So when we go back to this overly accurate answers to too many questions, we can see that by reducing the accuracy, we can handle more questions. And this is the trade-off between having smaller privacy loss and larger errors. So we can understand and control the cumulative privacy loss over multiple computations. And as a result, differential privacy is programmable. Given a toolkit that has differentially private sort of primitives for simple computations, you can then combine them in creative ways to get differentially private algorithms for much more complex statistical analyses. So it's a lot like programming. I mean, you know that everything that you can compute with ands and ors, but that's not how anybody thinks, and it's not how anyone programs. We build certain primitives and then we construct complex algorithms that combine these primitives in creative ways in order to minimize certain kinds of costs like time and space and so on. And the same thing is true in differential privacy, only we are also trying to minimize cumulative privacy loss. So all of this follows from the fact that differential privacy is closed under composition. So let's give a technique, a simple technique, which is called the Laplace mechanism. And this is just the addition of Laplacian noise. So in order to explain this mechanism, I need the concept of what's called the sensitivity of a function. So let's say that f is some statistical analysis or some function, like what fraction or how many people in the database like to play the violin. And the sensitivity of the function f is the maximum over any pair of databases that differ in just one element of the value of f on one of those databases and the value of f on the other. So for this counting query, how many people in the database like to play the violin, the sensitivity is 1. So if I would like to publish the value of the function f on my database in a privacy preserving way, then what I do is I draw noise from the Laplace distribution, which is pictured here on the right for various settings of the property of the parameters, with mean 0 and with standard deviation delta 1 over epsilon. So let's take a look at that. As the sensitivity is, if the sensitivity is large, then I need a lot of noise to cover or hide the presence or absence of any one individual in the result of applying F to the database. So here's the sensitivity in the denominator where it belongs. If the sensitivity is large, I'll be adding more noise. Epsilon is my privacy loss parameter, and we saw that the privacy loss is smaller when epsilon is smaller. And there's epsilon in the denominator, which says that I have to add more noise if I want to have small privacy loss. So you can see that the scales here, you know, the things are behaving in the right way. So to release the value of the function f in a privacy preserving way, we compute f on x, and we take a draw from this distribution and we release the result. Okay. Now, we talked about counting queries. The sensitivity of a counting query is 1, and we tend to think of epsilon as a constant. So the counting query then requires noise, privacy preserving counting requires noise that roughly is scaled to 1. 1 over epsilon is constant. What if I wanted to ask about K counting queries? So how many people like to jog? How many people like to play the violin? How many people like to read books, and so on? Actually, almost the same theorem holds. What we need to do now, though, is we need to redefine the notion of sensitivity. We're sort of asking, in this particular way of framing things, we're asking about K different queries, and each person could conceivably change the outcome of each of those K queries. Somebody, if you add somebody new, that new person might like to play the violin and to jog and to read books. So a sensitivity of 3, if you define the sensitivity in this way as the L1 difference between f of x and f of y. And so the theorem is essentially the same, although you now need to add noise that is scaled to the new sensitivity, this expanded notion of sensitivity divided by epsilon, independently drawn to each of the different answers, each of the different K answers. And so now for each answer, since delta 1 itself is K, we're adding noise that looks more like K. K over epsilon, epsilon is constant. Okay. Another way that we could have gotten to this is through composition. If we increase the privacy to epsilon over K for each of the K counting queries, then since at worst the epsilons add up, the cumulative privacy loss would be epsilon. All right. But here's something very interesting. So let's think about histograms. So histograms or contingency tables are sort of the workhorse of official statistics. And a K-cell histogram takes the space and it divides the space into disjoint regions, and it asks for each region how many people in the database are in each of these regions. So for this query, even though the number of regions K could be very large, the sensitivity is just 1 still, because the addition or deletion of any one person can affect the count in only one cell, and it can affect that count by only 1. So the sensitivity is 1. So if you have a histogram query, then you can add noise that's scaled to 1 over epsilon rather than K over epsilon in each of these counts. So when Adam Smith told me about this example, that's when I realized that sort of something new was happening here, that something very, very interesting was happening. So just a small detail on this, I didn't formally define exactly what privacy loss is, but I want to sort of tell you privacy loss can be negative. So we think of privacy loss as always positive. Every time something is asked, information about me is leaked. But that's not entirely true. So suppose, for example, that there's a count of something. If I'm in the database, the count is 20, but if I'm not in the database, the count is 19. Okay. Now, suppose I'm in the database. So the true answer to the query would be 20. But we get a response, like when someone asks, they get a response that's less than 19.5. So what I have here are the two probability distributions on outcomes for the Laplace mechanism when in the red case is the database that includes me, and in the blue case is the database that doesn't include me. If the truth is 20, but we get a response that sort of is more likely when I'm not in the database, when the answer is actually 19, then privacy loss turns out to be negative. We're getting, yes. In some sense, the adversary is being thrown off the scent of the true answer. And that's nice. And in fact, the expected privacy loss turns out to be epsilon squared when the mechanism is epsilon differentially private. And this is a big win when epsilon is less than 1. And in fact, if you, sorry about that, forget about the third bullet. You do get a privacy loss, but that's not, yeah, okay. You get a privacy loss that's very tightly concentrated around its mean. This is actually true. And this will give rise to a lot of powerful relaxations of differential privacy. So what we really get is this kind of random walk on the actual privacy loss. So there's another important model that I wanted to mention to you because it comes up so much in the real world. And this is called the local model. So think about a server with a whole bunch of clients that are elsewhere. And in the local model, privacy is sort of rolled in before data are collected. So getting back to our flossing example, did you floss last night? This is a protocol, which is also known as randomized response, and it dates back to Warner in 1965. And it goes like this: flip a fair coin. Here are your answers. Here's how you should go about telling me your answer in a privacy preserving way. Flip a fair coin. If you get heads, don't tell me, but you will respond yes and no otherwise, but don't tell me yet. Sorry, if you get heads, you need to flip again. Don't tell me that you got heads, but you need to flip again. And if the second coin is heads, then say yes. And if the second coin is tails, say no. On the other hand, if your first coin came up tails, you'll just answer honestly. So the privacy analysis is pretty straightforward. And basically, if you look at the probability that you say yes, given that the truth is yes, divided by the probability that you say yes, given that the truth is no, that ratio is 3. And similarly, the probability that you say no, given that the truth is no, divided by the probability of no, given that the truth is yes, that's also 3. So this is a log of 3 differentially private algorithm, and that corresponds to an epsilon of about 1.098. And if you're trying to figure out on a set of size S, how many people in the data set actually flossed last night, you can reverse engineer the noise to learn the approximation to the true flossing fraction, and your estimate will be off by only an expected sort of square root of S, or square root of little n in this version. And if you wanted to make this more privacy preserving, so you wanted to change the value of epsilon, you would flip a biased coin and you would recalculate taking bias into account. So you force the ratio of the 2 probabilities of answers closer to 1 by answering honestly with much smaller probability. Okay. So why did I mention the local model in particular? Well, one reason is that it's deployed all over the place. It was very, very popular in industry with the first implementations of differential privacy on an industrial scale was in Google's report published in 2014. And industry likes it because it sort of pushes the trust boundary out to the client. There is a privacy, an accuracy loss. We had errors that looked like square root of the size of the database for counting queries in the randomized response model, whereas we had answers that were off by a constant amount in the, when we used the centralized Laplace version. So people do prefer the centralized model, and as industry has become more bold, it's starting to use it in the use differential privacy in the centralized model. And there are a number of platforms now in industry as well, many of which you would have access to. Okay. So one use of differential privacy very recently is in publishing information about changes in mobility in response to stay at home or work from home orders in the age of COVID-19. So this is an example from Facebook's blog on COVID-19 changes in mobility reports. Here are 2 different California counties. Each strand in each of these pictures represents a county, and the strand in gold is the county named above. And then this is an example from a Google website describing Google's COVID-19 changes in mobility data set, showing you the kind of information that you can have, like changes in retail and recreation, changes in grocery and pharmacy. Okay? And all of these are done with differential privacy. So this year, for the first time, the US Census Bureau will use differential privacy as its means of disclosure avoidance. As noted earlier, differential privacy, the census was the original motivation for our work on privacy. And I think it's really important to step back for a minute and think about how central the census is. It's used for allocating hundreds of billions of dollars, federal dollars. It's used for allocating the seats in the House of Representatives. It's used for implementing the Voting Rights Act. And like voting, census is located at the very heart of representational democracy. And like voting, it affects long-term outcomes and the distribution of public benefits via the flow of federal dollars to state programs that underwrite the common welfare of all of us. An accurate tally enables legislators and other public servants to assess whether specific locations are adequately served or are underserved, where best to place hospital services, ambulance services, post offices, parking lots, libraries, bus stops, and on and on. And the potential harm of a privacy violation in the census could be very severe. So for example, the discovery of a violation of the conditions of a Section 8 subsidized rental, housing assistance for which a family may have waited years, can result in an eviction and homelessness. So a government whose immigration and customs enforcement directorates have contracted with Palantir to find illegal aliens for deportation is surely capable of contracting for Section 8 and other zoning enforcement for the political mileage no less than for the money saved. So what happened? Well, the US 2010 census. This is John Aboud, the chief scientist and associate director of research and methodology at the US Census Bureau. And basically from a talk that Aboud gave, the techniques in the 2010 census do not suffice. Technical advances revealed a new vulnerability, allowing people to reconstruct data from tables that were previously assumed to be privacy preserving. So what did census do? They launched an attack. That is to say, they look, so the census publishes about 11 billion summaries and tables, so statistics and tables. So they launched an attack using the database reconstruction theorem, or the fundamental law of data reconstruction, on the published statistics. So they did a database reconstruction for all of the people in the 2010 census, and they linked reconstructed records to commercial databases that were available in 2010 to acquire personally identifiable information. And that gave them putative re-identifications of these different records. And they compared the putative re-identifications to the confidential data that the census really did hold. And they found that it was correct for 52 million people. And so in this particular attack, the attacker could learn individuals' self-response on race and ethnicity. And you may think that you know someone's race and ethnicity, but it's quite interesting that people's race and ethnicity, as they report it, changes from census to census. So you're getting an insight there into how people are thinking, and also the race and ethnicity, say, of their children and their adopted children. So the Census Bureau takes this very seriously. There is a fiduciary obligation to protect information that is compelled, as the census data are compelled. You have to answer the census form. And equally importantly, everybody who runs surveys knows that they can't get accurate answers unless people trust, unless they feel free to answer, they feel that their data will be held safe. So here's what Aboud says: we fixed this in the 2020 census by implementing differential privacy. Was this met with jubilation? Hardly. So we'll take the last 2 minutes here to talk about some of the challenges. Researchers, like historians and sociologists, demographers and economists, aren't trained to interact with data in a differentially private way. Moreover, in part for that, and in part for other more bureaucratic reasons, rather than, in some sense, just releasing information with differential, in the simplest way with differential privacy, instead, the answers to the statistics are post-processed to create synthetic data. And the synthetic data are all sort of non-negative integer marginals. And this process is fraught. So the first experimental results on synthetic 2010 data were mixed at best. And in Aboud's words, in the Research Matters blog post he wrote from the Census Bureau, the privacy preserving error of the differential privacy mechanism is inherently unbiased and easy to control through policy decisions governing the selection and allocation of the privacy loss budget. However, the post-processing error, which workshop participants clearly demonstrated, introduces unacceptable and problematic data biases and distortions, and it requires structural and statistical changes to the disclosure avoidance system to mitigate. So they're working on it. It would be great if it were possible to publish the privacy preserving statistics without creating synthetic data. Also, analysts have to be trained to adjust for noise. You could be getting differentially private statistics, but you can't treat those as if they are just ordinary statistics. You have to do something to account for the noise. And with differential privacy, you at least can do this because the generation mechanism is known. And there's interesting and good work going on in the statistics community on precisely this kind of thing. But there's no getting around the fundamental law. It is a fundamental law. And what that means is that very small numbers can get occluded or get proportionally large error. And yet that has nothing to do with differential privacy. This is just true if you're going to have privacy. So if you're going to have privacy that will protect all individuals equally, there will be some loss. And that means that you have to figure out, how do you allocate your privacy budget? Where do you want to focus most of your accuracy? So I want to close with this slide. Look at the curve in gold. Normally people will draw, this is a cartoon, this is not a real graph. Normally people say, oh, if you have no privacy, you get the best utility. And as you increase privacy, your utility tanks. And they say the thing to do is to look for some nice point in the middle. But I think this is not a completely accurate story. I think that if you have no privacy, if you offer no privacy, then the people who feel most vulnerable will not answer, or they will be even more disinclined to answer. So the risk of confidential data leakage imperils trust. Think about the hospitals in your vicinity. If even only the most vulnerable in your community decline to be counted, this still will translate to under-provisioning and reduce the utility for you and for everyone. So I think it's very important, as we figure out how to move forward, to keep in mind that the real picture is not that curve in gold, but is more like this, this picture in blue. And with that, I'm going to skip to the end and take questions.
Yeah, thank you very much for a great talk. We are now in the question and answer session. I would suggest that everyone who would like to ask a question, put this in the question and answer part of Zoom. And there are already certain questions coming in. So the first question is by Brian Logri. He asked, if there are multiple adversaries collaborating and M, so the mechanism is unable to detect this, does this mean that one cannot control the differential privacy loss across the collaborating adversaries? If so, are there ways to—
Let me answer. The answer is, it's a good answer. The answer is that we abstract the adversary or the analyst so that it is the database against the world. And you could think of our analyst as being a union of many different analysts who are all working together. And in fact, differential privacy composes automatically and seamlessly, even if you have a bunch of different data sets. And the data sets are operating independently of one another, up to the sort of, yeah. So the composition theorems are very strong.
Okay, thank you very much. So the next question is from Aviva Prince. And she would like to know, if you don't know how many counting queries will be submitted, can you use the Laplace mechanism with k equal to 1, 2, 3, and so on as the queries come in?
So what you can do is you can reduce your added privacy loss as the queries come in. So let's just take the simplest case. Let's just say, suppose we're taking epsilon equals 1 for simplicity. You spend privacy loss 1/2 on your first query, 1/4 on your second query, 1/8 on your third query, and so on. But the noise will start getting large. Better to allocate for some large blocks. But so you can decide how much you're going to dip into your privacy budget reserves each time a new query comes. But you have to have fixed but you can't keep going. If you've decided a priori that the maximum privacy loss you want to tolerate is epsilon because that's the right setting for you, then you have to be sure that that's the cumulative loss.
Okay, thank you very much. So then there's one question actually by Ashish.
So thanks a lot for a very exciting talk. This question is related to a question that got asked earlier. So as you know, data portability, where consumers can easily share their data on one platform with another platform, has been suggested by many regulators as an important component of consumer rights, especially in Europe. And in view of the question about multiple adversaries, how does this interact with privacy, if at all? And do you know of approaches that can address the privacy concerns that might arise with data portability?
So a priori, I don't see a problem with data portability and what we're talking about. I love the question. I haven't thought about it a lot, but I don't see a problem. So in the full description of how composition works, we have a series of rounds, and at every round, the adversary gets to choose a pair of adjacent databases of her choice. And so this portability thing would just be a special case, and we would still be controlling the cumulative loss. So as I say, a priori, I don't see a problem.
Okay, any more questions? I don't see any more at the question and answer part. There's one question. So this is again by Brian Lockery. He said, I see a distinction between the notion not in the data set versus never existed. A person's existence can change the population and therefore reveal something about them. Is this distinction relevant and or addressed?
So, Brian, I'm not quite sure what you have in mind, but sometimes when I have talked about this, I talk about sort of real people versus ghosts. And in the end, you can't tell whether someone is a ghost or not. So I'm actually not, I'm not sure that I totally understand your question. But my guess is, so guessing at what your question means, I think differential privacy does not have a problem with it.
Okay, thank you. Any more questions also from the, let's say from the panel? If not, then I would now hand over again to Ashish.
So once again, thanks a lot, Cynthia, for giving this exciting talk. I think this talk epitomizes how one can do data science and theory and algorithms at the same time, be a full participant, a full citizen of this world, and a participant in both policy and the philosophy that governs our digital society as we move forward. So unless there are additional questions, I think, or additional comments from Cynthia, I think we'll stop this webinar. Thanks a lot to the organizers and especially to Geeta.
I'd also like to mention that we'll have another plenary talk tomorrow morning at 10 a.m. Pacific Daylight Time, and that'll be Jennifer Chase of the University of California at Berkeley, who will be speaking on graphons and machine learning, modeling and estimation of sparse networks at scale. Everyone, thank you so much for joining.